All right, so we've talked a lot in this part of our unit about characteristics of acids and bases, how to qualitatively distinguish between them, how to quantitatively distinguish between them. But what I want to look at right now is how the structure and how the atoms that are connected in making the acid are going to influence the strength of that acid, and comparably, its conjugate base, what the strength would be of its base. So for binary acids, the characteristic that plays the primary role is the strength between hydrogen and the anion, its bond strength. And this is going to play a really significant role when we're looking at anions that are coming from the same group. The more polar that bond is, the easier it is to dissociate the hydrogen from that anion, and that's going to increase the strength of that particular acid. There is one notable exception, and you see that over here in the example, and that would be HF. The most electronegative halogen is fluorine, so it would have the greatest electronegativity difference between hydrogen and fluorine, and therefore would have the most polar bond. HCl would have the next polar bond, most polar bond, HBr, and then HI. But the HF bond is not easily broken because fluorine is, again, so electronegative, it does not handle having that connection broken nearly as easily as the other halogens in the group. So because hydrogen is, or sorry, as fluorine is bound and determined to hold on to its electrons, HF is classified as a weak acid, and is what we observe when it is added to water, is that it only dissociates partially. Um, but the others are going to follow the trend where the more polar the bond, the greater the dissociation. And we would see this with our weak acids as well. So if you look at group 16, H2S would be a stronger, weaker acid than H2SE. When it comes to oxyacids, those that have oxygen attached to that halogen, the amount of oxygens that are attached is going to have a significant role in determining that acid's strength. And the reason why is that oxygen is just as electronegative as the halogen. And so the more of those oxygen atoms that are attached to that nonmetal, you're creating more of a polarity between that negative portion of the acid, the anion, than you are between than what would be present if you just had chlorine pulling at the oxygen attached to hydrogen. So additional oxygens is going to help to polarize that bond, pull the electrons away, and make it easier to break it. So we see in these examples here, HOCl or HClO is going to be the weakest of these four oxyacids. And then HClO4 is one of our six strong acids. HOClO, HClO2 is going to dissociate more than HClO, and HClO3 is going to dissociate even more than that. But the only one that's going to completely dissociate is the one that has the four oxygens attached to the chlorine atom. I will not ask you to compare something like HClO2 and HBrO4, but I could ask you to compare HClO2 to HBrO2, or I can ask you HBrO2 to HBrO3. We're going to talk about how we compare them when you have an oxyacid and the same number of oxygens in this next slide, and that deals with the electronegativity of that central atom. When you start to add on oxygens, again, you have the H connected to the oxygen and then connected to the halogen, and any other oxygens are going to surround the chlorine, the bromine, or the iodine atoms. If that halogen is more electronegative, it's going to help to pull the electrons more towards its side of the bond than leaving them with oxygen. So as we talked about previously, chlorine has a higher electronegativity than bromine, which has a higher one than iodine. So whether it be HIO, HBRO, or HClO, whether it be HClO2, HBrO2, or HiO2, you're going to see the same general trend. The less electronegative that halogen is, the less acidic that oxyacid will be for the same amount of oxygen atoms if the only difference is the halogen that they are bonded to. And so here we've got two oxyacids, HBrO2 and HClO2. They both have the same number of oxygens, so we want to look at that halogen to determine which one is stronger. The one that has creates a more polar bond that has a greater electronegativity difference is going to help to make it easier to break that bond. It's going to help to distribute the electrons asymmetrically more. And we would see that with HClO2 because Cl is more electronegative, more polar than bromine. And since the more polar you are, the easier it is to break your bond, the more acidic you will be. HBr2 would be less acidic than HClO2. You can write down as much or as little of this as you would like. Here we're looking at two oxyacids, but they're the same nonmetal bonded to the oxygens. We have a different number of oxygen atoms. The more oxygen atoms you have, the greater the polarity is placed on that HO bond, and so the easier it is to break. So H3PO4 is going to be better capable of destabilizing that HO bond by pulling the electrons more towards the side of the molecule with oxygen atoms than towards the side with the hydrogen. And then finally we have these two bases here. So if we're wanting to destabilize a bond to be able to break the hydrogen off of the acid, with bases we want to stabilize it. We want to accept those protons. So which one of these is going to be able to be more effective as a base? Well, more oxygens is going to create a greater polarity. We want a smaller polarity. We want less polar to our ion so that hydrogen will stay attached to it because bases want to accept those protons. SO42 minus has more oxygen atoms than SO3. Because it has more oxygen atoms and is better capable of destabilizing that HO bond, it is not going to be as willing to accept the hydrogen ions. It's just going to let it go again. So SO32 minus would be a more effective base because it is going to have a less polarized bond and therefore would be more capable of accepting those protons. And then the final example, we have two acids that are conjugate acids of their bases, NH4 plus and PH4 plus, and we're given the bond energies between these, that NH has an energy of 391 kilojoules per mole and pH has one of 322 kilojoules per mole. Acids again want to donate protons, and to break that NH bond you would need 391 kilojoules, while to break a pH bond you would need 322 kilojoules. Well, if you want to make it more capable of donating protons, you're going to want to use up less energy because that's going to make that happen more quickly. So as a result, NH4 is going to be less acidic than PH4 plus because it is going to require more energy to break its bond, and therefore it's going to require more effort to donate that proton.